This year, 2015, is the 100th anniversary of general theory of relativity. It's also the 100th anniversary of Noether's theorem. These two ideas have really made an impact in modern physics. General relativity essentially is our theory of geometry in space-time. It tells us that the presence of matter in space-time tells space-time how to curve, and conversely, the curvature of space-time tells matter how to move. So the dynamical response of presence of energy or matter in space-time is what gives us gravity. So this is one of the fundamental insights in nature. And as we've seen earlier today in Robert's lectures, symmetries also play an important role in understanding physics, and these symmetries are really informed by Noether's theorem, which associates conserved charges to these symmetries. So it's a spectacular coincidence that all of this happened 100 years ago. I'd like to tell you a little bit about certain solutions to general relativity that were first found 1 year after Einstein introduced his theory, and discuss some features of these particular solutions to general relativity. So the equation that defines the subject is G mu nu equals R mu nu minus 1/2 G mu nu R equals 8 pi G Newton over c to the 4th T mu nu. So I'm going to be pedantic and keep factors of C and H bar. I'm doing this for a reason. I want to distinguish ultimately between what are classical effects and what are quantum effects. So it's useful to keep these guys around in order to do that. So the left-hand side of the Einstein equation, this guy here, is basically a state of geometry. And this right-hand side is stress energy associated with matter. So we're going to look at particular solutions to this equation. This equation is a second-order, nonlinear partial differential equation. Such equations are notoriously difficult to solve. The best technique anyone has is to guess the solution and check that it works. So in 1915, when Einstein proposed general theory of relativity, he had one solution to the system of equations, which was empty flat space. So it's a very boring solution, but in 1916, 1 year after the theory was first proposed, a fellow named Schwarzschild developed the second solution. The second solution is the black hole solution. The behavior of the solution is also the geometry associated to a mass, for example, the sun, when you're far away from the mass. So I'm working in flat geometry. There's no cosmological constant. And if you look at this equation, one of the things we can do is take a trace of both sides. If we take a trace of both sides, we basically hit this equation with the inverse metric, G mu nu. In doing that, I'm working in 4 dimensions. So G mu nu on R mu nu gives us R, and G mu nu on G mu nu gives us 4, the dimensionality of space-time. Similarly, G mu nu on T mu nu gives us a trace of the stress energy tensor, which are called T. So hitting both sides with the inverse metric, we find that R, the scalar curvature, is equal to minus 8 pi G Newton over c to the 4th T, which we can then plug back in this equation. That way we can get an expression in terms of the curvature on one side and T's on the other side. When we do this, we see that R mu nu is equal to 8 pi G Newton over c to the 4th T mu nu minus 1/2 T GV. So if there's no matter in the theory, the right-hand side vanishes. There's a stress energy associated to the vacuum is 0. And the vacuum Einstein equation then is R mu nu equals 0. So what Schwarzschild found was a solution to the vacuum Einstein equation by imposing spherical symmetry as an ansatz, and then he found the solution. Okay. So this solution is a metric. The metric looks like this. df squared is minus 1 minus 2 GNM over RC squared, C squared dt squared, plus 1 minus 2 GNM over RC squared inverse dr squared plus r squared d theta squared plus sine squared theta d phi squared. So this is the metric, the round metric on S2, which I'll call d omega 2 squared for shorthand. Okay? So this is a spherically symmetric solution. Is the gravitational field associated to a point mass if you're far away from this mass. So m is the mass, and this is a solution. You can plug this metric in to this equation, and you find the right-hand side is 0. So it's an exercise to do this. As usual, you start with the metric, you define the connections, you define the curvatures, and you just verify that this tensor is a 0 tensor. Okay? So one can do this. It's more illuminating to just look at the properties of this metric. Okay? So that's what we'll do next. So I want to make some observations first. This observation is, suppose we send the mass to 0. So the mass to 0, this term goes away, and this term goes away. The metric is then just a metric of flat space, which is what we expect. Let's look at what happens when r goes to infinity. If r goes to infinity, this term drops out, and this term drops out again. So again, at infinity, the metric is that of flat space. That property is called asymptotic flatness. It's a property of this metric. Okay. Now let's examine the metric and see where things can potentially go bad. So we notice that these terms here, which appear in the definition of the line element, go to 0 when 1 minus 2 GNM over RC squared equals 0. That is to say, when R equals RS equals 2 GNM over C squared. This RS is called the Schwarzschild radius. It's associated to the size of the event horizon of a black hole. Okay? Now, there's another place where this metric can go bad. This metric can potentially go bad as well at r equals 0 when this term blows up. Okay? So you want to consider the effect of these potential singularities that appear in this metric. I say singularity because something may be blowing up. For example, if this term equals 0, we have 1 over 0 in this organization, this space-time. Maybe that's bad. It turns out that r equals rs is not bad at all. It's in fact just a coordinate singularity, meaning with a cleverer choice of coordinates, you can find something which is smooth. Okay? So r equals rs is a coordinate singularity. But r equals 0 is a physical singularity, and it's something that no choice of coordinates can remove. So we say that a black hole is a singular space-time But the singularity is shielded to us, from us, by a horizon, which sits here. And I'll show you what a horizon means momentarily. Okay? So, how do we know this coordinate singularity is not a problem? What we can do is we can look at curvature invariants and see that they don't blow up at this coordinate singularity. So, a curvature invariant we can construct is just R, which is equal to G mu nu, R mu nu, as we wrote earlier. But R mu nu equals 0. R equals 0, and this doesn't tell us anything. But suppose we look at R mu nu rho sigma, R mu nu rho sigma. Take the Riemann tensor, we contract all the indices, and we obtain something which looks like 12 Rs squared over R to the 6th. So at R, little r equals Rs, this equals 12 over Rs to the 4th. 12 over Rs to the 4th is just some number, and it's perfectly finite. So the curvature invariant should be heading nicely at R equals Rs. There's nothing special going on there. We expect curvature invariance to blow up at a singularity. In fact, you can write down any curvature invariant in this geometry, and you'll find that R equals Rs is a finite quantity. Okay? So R equals Rs is perfectly tame. But R equals 0, for example here, if you set R equal to 0, this is blowing up. Okay? So, what can we say about these physical singularities? Well, we can say that the theory is problematic there, and we fix this problem. That's essentially the subject of quantum gravity. So far, we've taken general relativity as a classical theory of physics. We haven't made any mention of quantum physics in this story, and we know that general relativity is at the end of the story. We know there's quantum mechanics, we know quantum mechanics gets promoted to quantum field theory, and we should try to reconcile the nature of the singularity in a fully quantum mechanical theory of gravitation. We don't have a fully quantum mechanical theory of gravitation. We have candidates for a fully quantum mechanical theory of gravitation. The best candidate will be string theory, and we hope string theory has something to say about these physical singularities. So one of the subjects of these lectures is, I hope, to get to understanding the nature of these singularities within string theory, in particular examples of highly symmetric black holes in higher dimensions. Okay? Any questions? I'm being very heuristic here. I'm just telling you the story about what happens. So please interrogate me and ask me to explain details if you want to see them. Yeah.
So you said earlier that at the Rs, when R is equal to Rs, then you've got some kind of horizon. So when you do the coordinate transformation, then that is not there. I mean, the horizon is not there. So that means that there will not be, in that coordinate transformation, there will not be some kind of defined horizon?
There is still a horizon there, but this coordinates, you can find coordinates that go through the horizon.
Okay.
Questions? Come on, there should be some questions. It's the theory of relativities of black holes. It should be something which everyone wants to ask questions about. Yes?
So the change of coordinates that irons out the apparent horizon, does that mean you could peer into the black hole?
Sorry?
You said you could find a coordinate system which removes the horizon.
No, I didn't say that. I said you can find a coordinate system that goes through the horizon.
Does that mean you could look into the black hole?
No, once you go through the horizon, you're stuck there.
Oh. Okay.
Yeah.
I have a question. If I don't know anything about this general relativity, how can you put me in the picture, if you would?
Well, theories of physics are tested. So you can construct a theory of physics, and you need the theory that you construct to be consistent with all the measurements that are ever made. So historically, Einstein developed this theory, and he noticed that it made a prediction, made a calculation for what the precession of the periodic unit of Mercury is. that fit the observation, Newton's theory was unable to explain the slight deviation in where Mercury was predicted to be where Mercury was in the sky. Einstein's theory explained this. It was a factor of 2 roughly. The other thing is Einstein's theory made a prediction. The prediction it made was when in the presence of heavy mass, space-time curves. Because space-time curves, you can imagine a situation where there's a star here, a star out here, and the Earth is here. So the light, because the space-time around the sun is highly curved, the light bends and comes to us here. If we extrapolate this back, we would think the star was there. So Einstein's theory made a prediction for the angle at which light is deflected. That prediction was corroborated by Eddington when he went on an eclipse expedition to measure precisely this. So Einstein's theory is a theory which relates matter to geometry. It's a theory that makes predictions. It's a theory that's tested, and consequently we have reason to believe it. Does that answer your question?
Yeah, thank you.
Yes?
Sorry, Vishnu, I'm not sure whether this question gets any physical meaning, but I'm just thinking, what, the case where m goes to infinity has it been x and is it something that makes sense to
No, I don't think it makes sense. Send the mass to infinity. I mean, you can think about so very close to this this black hole. You can think of masses that are much lighter than this mass, and work in a post-Newtonian approximation and compare physics when m is much bigger than a test mass m. That's sort of a limit in which we're sending m to infinity, and we can see what's happening here. But in terms of the metric, setting m to infinity as a parameter, I don't think that makes sense. Okay. Other questions? Very good. Let me heuristically sketch out for you what the event horizon is. So to make this heuristic sketch, I just need classical mechanics. So suppose you were sending a rocket from the Earth to the Moon. This rocket needs to have escape velocity in order to escape the attractive gravitational well of the Earth. So we have 1/2 mv escape velocity squared as the kinetic energy of this rocket. This plus the gravitational potential energy equals 0 to infinity in order to escape the attractive pull of gravity. So we can solve for VE, and VE is square root 2 G and M over R. Okay? Now suppose there's an object so massive that the escape velocity was the speed of light. Then R is 2gn m over c squared, which is the formula here. Okay. So the escape velocity in classical gravity is essentially the surface beyond which you can't escape, because there's a speed limit that Einstein told us exists. This is the speed of light. So the horizon is a one-way membrane, if you like. Once you pass the horizon, you can't come back classically. I'm emphasizing the word classically because we'll see that there may be a way to come back, at least for some things to come back in a certain sense, quantum mechanically. So the horizon in gravity is a null surface. So what that means is that certain vectors that are defined at the horizon behave in a particular way. So what this means is that if we consider normal vectors to the horizon, these are null, meaning they have zero length with respect to the local Lorentzian metric that exists at the horizon. Yes?
So could you please explain why they are zero?
Okay, so what happens is, in this space-time, there's this minus sign. This minus sign means when you measure distances, they can be positive, or they can be negative, or they can be zero. So in Euclidean space, the metric is just ds squared is dx squared plus dy squared plus dz squared. So 2 points in the room, when you measure their distance, it's always some positive number. Because of the minus sign in these metrics, these Lorentzian metrics, you can have distances which are zero. So if you consider space-time with a minus c squared dt squared added in, then if we're plotting on these axes, we can use some colors. If we're plotting on these axes, the way light travels. Light travels on a cone. So the idea is that if we have, we call this my t-axis, my ct-axis, we call this my x-axis. Light travels at 45-degree angles on this picture, and the distance along this cone is always going to be zero. So if you look at what light is doing from the perspective of 2 points along this cone with this metric, you're going to measure a zero length. Those vectors are said to be null. Those lengths are said to be null. If you think about the horizon, you construct normal vectors to the horizon, it turns out they're all null. That's the meaning of the statement. That's a definition of the horizon, if you like. Okay. So I'm going to make a technical remark. This technical remark is useful in certain contexts, but for our purposes, since we know that the Schwarzschild radius, the horizon sits at r equals rs, these technical remarks are, well, they're just for the benefit of the advanced student. So I want to remark that how do you, suppose I just give you a metric. How do you know where the horizon sits? So I want to distinguish between two ideas. One is when GTT, the time component of the metric, vanishes, and when GRR, inverse RR component of the metric, vanishes. So this is called the static limit, and this is basically where the horizon sits. So the purposes of the Schwarzschild solution, these two are the same. But for example, for other spacetimes, these two needn't be the same. Typically, when you're solving for the horizon, you're looking at the inverse metric component in the RR direction. Okay. So there's in order to solve general relativity, so general relativity is just a set of differential equations. In principle, it emits a lot of solutions. You want to ask which solutions are physical. in order to determine which solutions are physical, you impose energy conditions on the space-time. So energy conditions are basically conditions on the stress tensor when contracted with various vectors. So consistent with the energy conditions you impose on the space-time, in order to get some physical results, physical geometry that's worth studying, there is a cosmic censorship conjecture. Cosmic censorship conjecture says that because singularities are bad, we need to avoid singularities in classical gravity. So the cosmic censorship conjecture asserts that when there's singularities in space-time, these singularities are shielded behind a horizon. Now, this works for black holes. It's a lot more mysterious when you consider an initial singularity, the Big Bang, whence we think the universe began. So the status of the cosmic censorship conjecture is not fully clear in the theory. But this is a conjecture. So the claim is that the fact that the horizon shields us from singularities is a consequence of the energy conditions you impose on the kind of solutions you admit as solutions to general relativity. Yeah.
Can you then assume that singularities occur within black holes?
Singularities exist within black holes, yes. So, as I said, the goal of the lecture, of these lecture series, is to explain, putatively, some scenario in which these singularities can be explained from quantum perspective. Okay? So that's where we're headed. Now, I want to make some other comments on this metric. There's a theorem in classical gravity called Birkhoff's theorem. Birkhoff's theorem says that this metric I've written down is a unique metric that's spherically symmetric that solves the vacuum Einstein equations. Okay? Okay, I also want to observe that the Schwarzschild metric is both static and stationary. The static and stationary are technical terms. One is a subset of the other. So static is a subset of stationary. For a stationary solution, what this means is there's a killing vector that is time-like at infinity. So in other words, at infinity is a well-defined notion of time translations. This killing vector is dt, and the metrics that are stationary can be written in the following form. They're time independent. So time appears nowhere in the metric coefficients. And we can write the metric as ds squared is g00 of the space coordinates dt squared plus 2g0i of the space coordinates dx0 dxi plus gij of the space coordinates dxi dxj. stationary. Stationary metric can contain in principle off-diagonal terms involving a time coordinate and a spatial coordinates. A static metric you can choose your coordinates such that these terms aren't there. So since our metric is diagonal, it's a static metric. There are no cross terms. And since time doesn't appear anywhere, it's stationary. So the metric functions have an r in them. They all have an r in them, in fact. This one's got an r and a theta in them. But time appears nowhere. So static spacetimes are stationary, and they're also invariant in their time reversal invariance, because dt squared maps to dt squared when you send t to minus t. Yes?
Can you just repeat what the stationary condition means?
Stationary condition is a metric that can be written in this manner. There's no time dependence explicit in these metric functions. And in principle, however, there could be a cross term involving time and the spatial coordinates. Static means the cross term is not there in the stationary solution.
And in terms of the Killing basis you mentioned,
So, if it's a stationary solution, there's a well-defined notion of time and infinity. So an example of a metric which is stationary but not static is the Kerr solution. The Kerr solution is a black hole with angular momentum, a black hole that's spinning on its axis. Yes, Warren?
So we like to use infinity to define our concepts. So we define a stationary solution as one with a time-like Killing vector at infinity.
Yes.
Why would we consider a time-like Killing vector at infinity as opposed to maybe a time-like Killing vector on the horizon?
Well, the horizon is the vectors all in all. It's a convenient way of looking at the space-time. So static is a condition which is more stringent than stationary. Static is telling us that so you can foliate your space-time with hypersurfaces, and the time-like Killing vector is orthogonal to these hypersurfaces which foliate space-time. It's a very stringent condition on the space-time. Stationary is a much looser condition. Just saying it's a well-defined notion of time and infinity. Okay? Okay, I won't write down the Kerr solution. I'll just say the Kerr solution is a black hole, which is also spinning. These are the black holes that astrophysicists and astronomers observe in the sky. So there are other solutions we can consider. These other solutions, for example, are the Rising-Nordstrom solution, which is a black hole with charge, electric charge, and the Kerr-Newman solution, which is a black hole with angular momentum and charge. Okay, so the other solutions I'm going to write down to the Einstein equations. Now, so you can think about a stationary solution as a solution which does the same thing at every time. A static solution does nothing at any time. That's another way of describing the distinction between static and stationary spacetimes. Okay? Maybe that helps. So if you have a solution which is the Kerr solution spinning, it's doing the same spinning at every time. A static solution, a Schwarzschild solution, does absolutely nothing. It just sits there. Okay? How am I doing on time?
16 minutes.
16 minutes. Okay. So Kerr solutions then have angular momentum, I'll call that J. Riemann-Nordström solutions have charge, I'll call that Q. And Kerr-Newman solutions have angular momentum and charge. All of these solutions, including Schwarzschild, of course, have mass. So we can make Birkhoff's theorem into a stronger statement. And John Wheeler made this statement, which he poetically called the no-hair theorem. So the claim is black holes have no hair. So what that means is the following. So I'm working in Einstein-Maxwell gravity in 4 dimensions. So it's Einstein gravity, meaning field equations are these equations here. It's Maxwell theory, in that we can have electric charges sitting around. So we consider this theory. The claim is that if you specify the mass, angular momentum, and the charge, you specify the metric exactly. Just knowing those values is enough to define the space-time. So in particular, you can consider 2 different states that you prepare. So for example, 2 different quantum states you prepare, psi1 and psi2. And they've got the same mass, the same angular momentum, and the same electric charge. Now we know that when we make gravity stronger, most systems shrink in size. So a solar system, you make gravity big, a stronger force, solar system's orbits will decrease in their radii. Most systems shrink when you make gravity stronger. So eventually you can take these states, you specify mass, charge, angular momentum, and collapse them to a black hole. When you collapse these different states to a black hole, the claim is you get the same metric. So these states could have been very different in character. They could have different shapes, they could have different colors, they could have different volumes, they could be intrinsically different states that you can distinguish in classical theory before the collapse. Once you get a black hole, the metric is the same, and the 2 states are no longer distinguishable. You don't know whether psi1 formed the black hole or psi2 formed the black hole, and information is lost to you. Content of the no-hair theorem is that once you know these things, you know the metric. There's no ambiguity about what the metric is, classically, once you specify these entities. So, quantum mechanically, this becomes very mysterious, and we'll address what this means in the next lecture when we discuss the information paradox. But classically, this is sufficient to specify a black hole. Yes?
Sorry, Vishnu, what you just said now is only true when the mass, the angular momentum, and the charge are the same.
Yes. You have 2 states with the same quantum numbers for mass, charge, angular momentum. They could be differently shaped. They could, be made of different materials. That information, once you form a black hole, is completely irrelevant. The metrics only specify the mass, charge, angular momentum. It's a very powerful statement. It's a very counterintuitive statement, but that's the statement. So, even in classical theory, we believe this was true in all dimensions. So it was originally stated in d equals 4 in asymptotically flat spaces. But we thought, until very recently, that this kind of philosophy, at least in the classical theory of gravity, extends to other settings. For example, non-flat, non-asymptotically flat spaces, the higher dimensions. So it turns out that's not true. So in 2001, the first explicit solutions were written that violated the no-hair theorem in 5 dimensions. So let me briefly sketch out what they did. So these guys who did this were Roberto Emperon and Harry Rial. So these are called the Emperon-Rial solutions. They're also called black rings. So the idea here is that gravity acts differently depending on what dimension you're in. So in 4 dimensions, the Newtonian potential is minus Gn mm over r. In d dimensions, this potential is minus Gn mm over r to the d minus 3. So gravity has a different characteristic fall off at infinity based on what dimension you're in. Now, suppose you're spinning something. You experience a centrifugal force when the thing is spinning. So for example, on a carousel or a merry-go-round, you experience this force. So the gravitational force, the gravitational potential, scales like, in 5 dimensions, G5 m over r squared. Okay? The centrifugal potential scales like J squared m squared r squared. This comes with a minus sign. This comes with a plus sign. You can imagine using centrifugal force to balance the attractive force of gravity. That's what these guys did. And they constructed what's called a black ring, which is essentially a donut in higher dimensions. So each of these slices of the donut is an S2, and there's a circle direction. So the horizon topology, which is what I've drawn here, is S2 cross S1. Whereas the black hole's horizon topology here was S2, and the equivalent to this black hole in 5 dimensions has an S3 topology. So instead of the natural spherical topology, you have some more complicated topology of balancing these forces against each other. This was only done in 2001. So even less than 2 decades ago, classical gravity has the ability to surprise us. We're learning new things about ordinary gravity in higher dimensions. That was very, very surprising to people in the field when these guys published that paper. So I also want to point out another peculiar feature of living in higher dimensions. So when things rotate, we usually think of them rotating about some axis. But you can really think about the rotation as being defined by the plane of rotation orthogonal to that axis. So in 5 dimensions, there are 4 spatial directions plus time. So you can have 2 planes of rotation that are perpendicular to each other. So a black hole or a black ring in 5 dimensions has 2 angular momentum. It can rotate independently on 2 different axes at once. That's something very unusual. It's very counterintuitive. I invite you to try to imagine it when you're falling asleep tonight. Picture a black hole rotating along 2 axes at once. So this S2 and this S1 have angular momenta J1 and J2 associated to them. You can think of as independent. So it turns out that with the same values of mass, charge, angular momentum J1 and J2, actually there's no charge in the story, mass, angular momentum J1, angular momentum J2, there are 3 distinct solutions. 2 of them are black rings. One of them is a fat black ring, where you think about the thickness here as being very big. One of them is a very pancake-like black ring. And the third is the black hole with topology S3. Given M1, given M, J1, and J2, you can find solutions with the same charges that have these 3 different behaviors. The 2 black rings, the fat one and the thin one, and the sphere. So the no-here theorem, which says that you specify the space-time uniquely, fails in D equals 5. We're continuing to examine the space of black solutions in higher dimensions. And we found that there are, other people have found that there are other interesting solutions. You can imagine a black Saturn, for example, a black hole with a black ring around it. That's also a valid solution to general relativity in 5 dimensions. So there's a whole spectrum, a whole zoo, a whole bestiary of black solutions in 5 dimensions that Emperor Henriot and their collaborators have explored pretty extensively. So I just want to point out these curious things happen in higher dimensions, and even classical gravity has the ability to surprise us even today, even 1 century after Einstein. So next time, I want to discuss black hole thermodynamics and discuss how black holes have properties of thermodynamic ensembles that you're familiar with. In particular, black holes have entropy. Now, when someone tells you something has entropy, they're really telling you there are quantum states in the system you can count. So, the natural question to ask is, if black holes have entropy, what does black hole statistical physics mean? And that question will lead us to the microstate picture for black holes in string theory, which I'll address in the third lecture. So in today's tutorial, we'll examine aspects of the Schwarzschild solution. In fact, we'll generalize the Schwarzschild solution to a space with a cosmological constant. Okay. Any questions?
So which dimension was the MLG Q only specifies spacetime? Is it only in D equals 4? Or?
D equals 4 asymptotically flat spaces. This is a theorem.
That's where it was only.
This is originally where it was formulated by Wheeler. And Wheeler's formulation, which is only working in 4 dimensions, was correct. It's just that everyone assumed this statement generalized to, say, anti-de Sitter spaces and de Sitter spaces and the higher dimensions. That assumption, which everyone made, was false. Yes?
You mentioned the black ring. What's in the middle?
Nothing. It's empty. You can go through the black ring. It's a donut. There's a geodesic trajectory in the space-time where the geodesic trajectory is that. You're not going through a horizon. Nothing stops you from doing that. Yes?
Is there a notion of a singularity?
Yes. This black ring has a singularity. Yes, that. In fact, the Kerr solution itself, a rotating black hole in 4 dimensions, is a ring singularity, not an point-wise singularity.
Once you go there, it's not.
Once you go there, space-time curvatures become large, and before you get there, you're ripped up by tidal forces anyway, so it's an academic question.